So I'm going to start off by having, at least in the beginning, a similar setup to what we had last week. So we're going to have f over f plus Cm extension. We're going to have L over QL, a finite extension. O will be the ring of integers in L. Lambda will be the maximal ideal in O, and F the residue field. And we're going to fix a character of GF plus valued in O cross, and this will be a continuous Theorem character. And what we're going to, so we're going to have a characteristic zero representation R. So it's polarized. And what we're going to, so we're going to assume that this is algebraic. So it's going to, that means it's Theorem and unramified almost everywhere. It's Theorem at the place of dividing L, unramified almost everywhere. We'll also assume that it has distinct Hodge-Tate weights. And we'll assume that a multiplier character nu composed with R is equal to this fixed character mu. And the Fontaine-Mazur-Langlands conjecture would imply that this representation R is automorphic. But like last week, we're going to try to show that under some extra conditions. So we're going to assume that there exists an automorphic representation pi such that R of pi, the Galois representation, is residually isomorphic to R bar. These are valued in the G of the residue field. And I guess we'll also want to assume that the multiplier of RL pi is mu. And so what I want to explain today is the following theorem. So suppose, first of all, that, so we need some condition on the residual image. So we're going to assume that R bar restricted to GF zeta L is adequate. We had this last week. And two, are going to assume either of one of the following two things. So the first is what I call Fontaine-Lafay. So this is the condition that the prime L is unramified in F, and and R and RL of pi are crystalline at each prime W dividing L, and moreover their Hodge-Tate weights are the same. So, and for all tau embedding F into QL bar, the Hodge-Tate numbers of R with respect to tau are equal to the Hodge-Tate numbers of RL of pi with respect to tau. So I'm just going to call this set of numbers H tau. And one more condition is that all of these Hodge-Tate numbers live between 0 and L minus 2. So we had this condition last week already, so I defined it. And so or we'll allow ourselves to be in the ordinary case. And what this means is that, well, I'll explain it later. I'll just say R and pi are ordinary at each W dividing L. So I'll explain what ordinary means in a little bit. And then the conclusion is that R is automorphic. So I should say that this theorem is due to Closell, Harris, Taylor, and a separate paper of Taylor in the Fontaine-Lafay case. And then I did the ordinary case in my thesis. And when we did this, we had this a much stronger condition in one called bigness, and this was relaxed to adequateness by Jack Thorne. So last week we had a similar condition where 2 was replaced by the condition that the Galois representation R pi connects to R at all of the ramified places. And so here, here you see that we have no sort of connects or strongly connects condition at places not dividing L. There's no condition at all there. And the condition 2 is only a condition at what's happening above L. So I'll say, before I say something about L, let me just remind you that the condition adequate implies R bar restricted to GF zeta L is absolutely irreducible. And this is if and only if L is bigger than 2 times n plus 1. So what about these conditions at the primes dividing L? So the reason for the Fontaine-Lafay condition is essentially following. It implies that the corresponding local lifting ring is smooth over O. So if we look at so we have here W place dividing L, and we look at the lifting ring corresponding to crystalline lifts with the same Hodge-Tate numbers as R and R pi. This is a power series ring over O. And so in other words, the connects condition is automatic, if you like. In the ordinary case, well, actually, so ordinarity, so what does this mean? So it's a purely local notion, so let's suppose K over QL is a finite extension. And we have a representation rho, an L-adic representation of GK. And we say rho is ordinary if it's isomorphic to an upper triangular representation where the Hodge-Tate numbers, well, first of all, each chi-I is Hodge-Tate or de Rham. It's the same thing for a character. And the the Hodge-Tate numbers increase as we move along the diagonal. So the Hodge-Tate numbers of chi1 is less than the Hodge-Tate number of chi2, and so on. These are for all embeddings tau of k into QL bar. So for example, something that looks like cyclotomic star 0, 1 is ordinary, because by our assumptions, the Hodge-Tate numbers of the cyclotomic character are -1. And then we say, so R is ordinary. So I've defined what it means for R now to be ordinary at all the places dividing L, and we say pi is ordinary at a place W dividing L if RL of pi restricted to GFW is ordinary. So let me just say this is more just of a working definition for this talk. There's actually a more intrinsic notion of what it means for pi to be ordinary in terms of Hecke operators having having eigenvalues which are L-adic units. So if you think of the case of modular forms, a modular form is ordinary at P if AP is non-zero mod P. It's essentially the same definition. And just make a couple of remarks. So the first is that ordinary implies Deformation. And the second condition is that, the second remark is that if each of the characters chi I is crystalline, then you might wonder, is rho crystalline? It's just built up out of extensions, and that's not true, but it will be semi-stable. Okay, so that's, and in the ordinary case, you can sort of analyze the corresponding lifting rings you get and show that they're sort of you sort of show that they're essentially irreducible, and so you're not too far from the case where this connects condition is automatic. But what I want to do today is try to explain the proof of this theorem in the Fontaine-Lefy case. Because I have assumed that the Hodge-Tate weights are distinct. Yeah, maybe it's probably not the most general definition. Maybe I could have put less than or equal to signs here. Yeah.
You might want to. Well, I don't want to suggest decorating the terminology anymore. It's
regular,
it's
ordinary.
But there's a whole. There's a theorem that the ordinary hypersurfaces are dense in the space of hypersurfaces, but they're almost never ordinary in this sense.
Yeah.
So what's the other definition? This one, strict inequality.
Pardon?
What's your definition?
For today's talk, I just want to assume everything is Hodge-Tate regular.
And strict, regular strict.
Yeah.
Another question: what does that mean in terms of the Fontaine-Veil-Delin parameter? Is it simple?
Well, the Veil-Delin parameter. So the finite, the R, so the representation of the Veil group with open kernel, will just be, will just capture how far each of these characters are from being crystalline. So the sort of finite ramification that you'll have. And then it's possible, for example, here it's possible that the monodromy is non-zero. for something like this. But if I had a higher power than 1 on the cyclotomic character here, if I had something like this, or 2, then n would force to be 0.
But in the general case, it's complicated. It will be complicated to compute the monodromy and stuff.
To compute.
The monodromy.
Again, if you know that the only way you can have monodromy is if basically the ratio of 2 consecutive characters is cyclotomic. But if it is, then I think it's hard to compute it. Mm-hmm.
One question. So when you assume that the residual representation is automorphic, do you assume that when you lift to the automorphic, the Hoptake bit type is the same as the Hoptake weight?
No. So in the ordinary case, the Hoptake weights are allowed to be different here. Is that what your the question? So in the Fontaine-Lefay case, I've assumed they have the same Hoptake weights, but here I just assume they're both ordinary. But it's essentially equivalent because there's a Heda family, so if you have a lift in one weight, you have a lift in any other weight, an ordinary lift. So I want to explain. So the proof in the ordinary case is essentially the same, except it's more difficult to explain because Heda families come into the picture, but somehow the underlying idea is the same. And so, as usual, we use solvable base change to make a few reductions. So as usual, we assume that all ramification takes place over places which split in the CM field. So there exists S, a finite set of places of F plus, which split in F, and such that S contains all the places dividing L and all the places where anything is ramified, so R is ramified, or mu, or pi. We can also assume that this pi is conjugate self-dual. This doesn't use solvable base. This just uses, to reduce to this case, just requires twisting. And that just means that the multiplier is cyclotomic to the 1 minus n. We may assume that there's I just say this is just using twisting. We may assume that there exists a unitary group of the form that we discussed last week. So this is a definite unitary group, quasi-split at all finite places. And the last thing we might assume, so far at the places away from L where R and pi are ramified, one of them might be sort of a lot more ramified than the other. So we want to sort of bring them to we want to sort of make sure that they both look, in some sense, we want to be able to compare them in some way. So we can make the following assumption. We can assume that for all places V and S, so where something is possibly ramified but V not dividing L, that if I look at the Galois representation, so for all V and S, as we did last week, we're just going to choose some place V tilde dividing V, place of F. So if I take one of these places where something is possibly ramified away from L, and I look at these two Galois representations, well, the condition is that after a base change, we can assume that these are unipotently ramified. So in other words, they both send inertia to unipotent matrices. So let me remark why we can always do this after base change. So this is true if and only if the corresponding Vedolin representations are of the form Rn, where R is unramified. And since R is only finitely ramified to begin with, we can always achieve this condition after a finite base change. And on the automorphic side, what does it mean in terms of pi for RL of pi to have ramification like this? The condition is that pi has Iwahori invariance. So what's this group? So where this Iwahori subgroup is the set of all matrices G in GLN of the ring of integers that reduce to an upper triangular matrix residually. So these are our reduction steps. And now we're going to follow the same sort of plan as last week. We're going to introduce Hecke algebras and deformation rings and so on. So we'll start with Hecke algebras. So first of all, we need to have a level. So we're going to let U, it's going to be an open compact subgroup of the unitary group, which decomposes a product over all places, where these groups UV are as follows. So away from S, everything's unramified, so we're going to take UV to be a hyperspecial maximal compact. At the places in L, we're looking at things which are crystalline, so this is a sort of unramifiedness condition. So we're going to take GLN of the ring of integers if V divides L, and if V is an S but doesn't divide L, we're in a case where we have Iwahori invariance. So we'll take the Iwahori subgroup, and this will be our level. I should say that there's a technical condition. Usually you have to add in some extra ramification at some other auxiliary finite place to make the subgroups what are called sufficiently small, which makes the sort of space of modular forms behave nicely. And I'm not going to mention it too much. Oh, sorry, and I even forgot a condition here. And I need to require, in order to introduce, for that auxiliary place not to mess things up, we need to assume that F doesn't contain the Lth roots of unity. It's just a technical point, so I'm going to ignore it from now on. And then as we saw last week, we have a Hecke algebra, which I called, so it's going to be generated by Hecke operators at places away from S. And this acts on a space of modular forms. And we have some weight, which I'll call A, and A just corresponds, A can be just determined in an easy fashion from the Hodge-Tate weights of the Galois representations. What else would we have? So we have a maximal ideal of T. So remember, this T is just a finite O algebra, O torsion free. And we have a maximal ideal. And in fact, I'm just going to call this guy T from now on. We have a maximal ideal M of T, corresponding to our residual representation, which we're assuming is automorphic. And we saw that this lemma of Carriol allows us to find a Galois representation Rm valued in the points of this group Gn at T localized at the maximal ideal M. And what this was essentially was the following. So we take a direct sum over all automorphic representation sigma prime on the unitary group, which have weight A and level U, so the same weight and level as pi has, and their Galois representations are isomorphic to our fixed Galois representation. And then the direct sum of these representations takes values in here, and the Hecke algebra T injects into this direct sum, and Carriol's lemma is that this direct sum of representations can be patched together into a representation over the Hecke algebra. So this is what we had last week. So now we want to turn to deformation theory. So that means we need to pick some irreducible components of the local lifting rings at the places in S. So for V dividing L, well, we don't have much choice. I've assumed I'm in the Fontaine-Lefy range. So CV is going to be the unique irreducible component of this Fontaine-Lefy lifting ring. And this is just a power series ring over O, so it only has one component. And for V and S, V not dividing L, so what sort of deformations are we trying to capture? Well, we're trying to capture those with exactly this property that they have unipotent ramification. So we take CV equals what I'll call CV comma 1. 1 is for unipotent. And this is the union of all irreducible components of the lifting ring. It's generic fiber. Consisting of closed points where, let me just say, where inertia acts unipotently. And you could rephrase that in terms of Vedolin representations if you want. Your Vedolin representation is an unramified R and some N. And then this gives us, of course, a global deformation problem. So this is the notation we had. So in words, we're looking at deformations which have this fixed multiplier. They're unramified outside S, and at the places in S, the lifts we get are factoring through these chosen irreducible components. So at the places in L, we're requiring that we look crystalline with fixed Hodge-Tate weights, and away from L, we have inertia acting unipotently. And of course, this is then represented by a universal deformation ring, and we get a map to the localized Hecke algebra, and this map classifies Rm, and it's surjective, as we saw last week. So now we're going to apply the Taylor-Wiles method. So I'm going to let our loc be the completed tensor product of the local lifting rings we've chosen at the places in S. So remember RCV, this is the maximal quotient supported on our chosen irreducible components. And I think we insisted it was reduced and O-torsion free. And then, as I explained last week, the upshot of the Taylor-Wiles method is the following, that there exists some integer g such that if we set R infinity to be a power series ring over R loc in g variables, then there exists a finite module for this ring R infinity. And we had a commutative diagram of the following form. So we have R infinity acting on M infinity, and the universal deformation ring was a quotient of R infinity by some ideal I. And if we take M infinity mod I, the same ideal, this is isomorphic to the space of automorphic forms localized at M. And the action up here is compatible with the action down here through the Hecke algebra. And the other thing we know is that the support of M infinity is a union of irreducible components of spec R infinity. Just remind you that to prove the theorem, it suffices to show that our lift R, sort of regarded as a point in spec of R of the universal deformation ring, which is a closed subset of spec R infinity, and it suffices to show that this is in the support of M infinity. And again, that's clear from this picture, because what this diagram says is that M infinity restricted to the global deformation ring is just the space of modular forms that we're interested in. So so for this point R to be in the support of M infinity, it's exactly the same as it being in the support of this space of automorphic forms. So remark, if RL pi connects or strongly connects to R at all V and S, V naught dividing L, then we're done. This was the case we had last week. So how bad can things be? So I just want to note that so the components, so R infinity is a power series ring over R loc. R loc is a completed tensor product of these local lifting rings. So to understand the components of R infinity, we have to understand the components of these rings. At the places in L, they're just power series rings. So all we have to worry about is what's happening away from L. So away from L, we have these unipotent lifting rings. And so this is here V naught dividing L, V and S, can have more than one component. So as an example, away from L. Oh, sorry, thank you. Yeah. E.g., if n is equal to 2, the norm of V is equivalent to 1 mod L. And let's just say the residual representation we're looking at is just a trivial representation. So if we're in this situation and we look at all unipotently ramified deformations, then this has two components. So one component is the unramified locus, and the other is Steinberg locus. So locus where things look like cyclotomic star 0, 1. And to arrange that R and R pi are on the same component in this situation is essentially the question of level raising or level lowering. So for example, if R lived on the Steinberg locus and R pi lived on the unramified locus, we'd want to raise the level of pi to put R of pi on the Steinberg locus. And level raising is difficult to do when n is bigger than 2.
So you have this local deformation, the local ring R square.
Yep.
What's the second one up there? Three lines up. I
Here?
understand CV, but what's the next thing?
This CV comma 1. That was this.
What was that?
That was the one was just supposed to be a reminder of unipotent ramification, the semi-stable things, yeah. So what we're aiming to show is that this point little r lies in the support of M infinity, and what the method of Taylor shows is the following. It shows that the support of M infinity in R infinity is actually equal to the whole spectrum. And then this, of course, suffices to prove the theorem because everything is in the support. So how does this go? So a reduction step is the following. It suffices to show essentially the same thing, but modulo L. So the support of R, so lambda was the maximal ideal in our coefficient ring O. So if we reduce everything modulo lambda, it suffices to show the corresponding statement. Okay, so it's obvious that if we have, it's obviously the thing we want implies this statement mod lambda, and now it's how do you go back? And so we use the following results. So the first is a lemma in commutative algebra, and it says that if, let's suppose, so we have R is an element of this category CO, so it's a complete Noetherian local ring with residue, or O algebra with residue field F. So I'm going to suppose that this is equidimensional and O torsion free. I'm going to suppose that M is a finite R module, which also is O torsion free. So in the application, R here will be R infinity and M will be M infinity. I'm going to assume that the support in R mod lambda of M mod lambda is equal to the whole spectrum. And lastly, that every prime of R that's minimal over lambda R, so in other words, an irreducible component of R mod lambda, the condition is that this contains a unique minimal prime of R. And then the conclusion is that what we want, that the support of M is all of spec R. So this fourth condition here is saying that every irreducible component mod lambda determines a unique characteristic zero irreducible component. And since we're starting with something that's O torsion free, the minimal primes in the support essentially should have characteristic 0. And so if you combine this with this fourth assumption, you see that they all must be in the, all of the characteristic 0 irreducible components must be in the support. And then Taylor shows the following proposition. So let me just call this condition here star. That the lifting ring, oh, I already have a notation, this unipotent lifting ring satisfies the assumption star. And also, I guess that this property is preserved under tensor products, so R infinity will satisfy this. And I'll just remark that M infinity is O torsion free by construction. So this is the end of the reduction step and reduces us to showing this statement mod lambda. So how do we do that? So the idea is to introduce an auxiliary deformation problem, which is going to look irreducible in characteristic 0, where everything is going to work nicely, but modulo L, it's going to look like this one we started with. So have to introduce some auxiliary data. So we may assume that for all of these places V and S, V naught dividing L, that the norm of V is equivalent to 1 modulo some high power of L, again by solvable base change, and we may assume that the residual representation is trivial. And now we're going to choose chi v. So this is going to be an n-tuple of characters from the ring of integers in OFV cross to the n, valued in 1 plus lambda O. So in other words, it's going to be, we're going to get units in O that reduce to 1 modulo lambda. And we're going to choose these such that the chi vj's, as j varies, are pairwise distinct. So we need, essentially we just need this power of L to be bigger than n in order to be able to choose these so that we get distinct characters. And now we're going to introduce a new deformation problem. So we're going to let C chi v be the union of all irreducible components of the local lifting ring consisting of closed points rho, with the Veda-Lean representation of rho being Rn, and R restricted to inertia is just given by this tuple of characters composed with the Artin map. Okay, so we're just fixing exactly what this finite inertial action can be. And then let me just remark that this implies that the monodromy operator is equal to 0 because these characters are all distinct. And the key proposition is that so if I look at the maximal quotient of the lifting ring supported on this union of components and O torsion free and reduced, then this ring is irreducible. And when I reduce mod lambda, it becomes isomorphic to the unipotent lifting ring modulo lambda. So this is not perhaps obvious as I've defined these rings, but it's at least plausible precisely because these characters are reducing to the trivial character modulo lambda. So modulo lambda, this condition is going to imply that we have unipotent ramification. So the idea now is to apply the Taylor-Wiles machinery simultaneously for the two deformation problems. So we have the sort of unipotent deformation problem at V and S, V not dividing L. And then the other problem is the deformations of type chi V at V and S, V not dividing L. So let me just remark, in order to apply the Taylor-Wiles method, you need to assume that you have a modular lift of the required type. So there exists a pi tilde such that RL of pi tilde so it's going to be unramified away from S. It's going to have the right multiplier character. It's going to be crystalline, same Hodge-Tate weights. H tau above L. So all these conditions are the sort of same as for RL of pi, but the last condition is that it's going to sort of land in this deformation problem at the places in S. So it's going to be, I'll just say, of type chi V for V and S, V not dividing L. So what we end up with is I was going to I thought I might have time, but I think I have time. So the basic idea is that you write down the space of modular forms of weight A type chi V at these places, and you show that this modulo lambda is isomorphic to so here we're just looking at things with Iwahori invariance, and here we're looking, so remember these spaces are defined in terms of functions. So we had functions f to some sort of Weil module, and they satisfy a certain condition. You just impose that sort of for U in the Iwahori subgroup. I think you require something like something like this. So you can regard these characters chi as a character of the Iwahori subgroup, and you just make an explicit definition of the space of modular forms like this. And because these characters are trivial mod L, you get this, and this is compatible with the Hecke operators away from S.
Do I understand correctly? You are not saying anything about the Galois representation associated to pi T and stuff, right?
That's what this condition here means.
Yeah, yes, but it's not related to...
Oh, I should have said, yeah, sorry, it's the same.
The same method.
And that's, I mean, the maximal, this maximal ideal M is in the support over here, so it has to be in the support over there. I mean, I guess this sort of trick appears in the work of Skinner and Wiles to do level lowering, if you've looked. It's a sort of similar idea. Okay, so the upshot is that we apply this Taylor-Wiles method similar.
Maybe one more stupid remark. I mean, is it a bit like somehow changing a Nevitype's character that's concrete?
Yes. Yes. Yeah. Yeah. Exactly. Yeah. So now we have the sort of following picture. So this is what happens when we apply the Taylor-Wiles machinery for this auxiliary deformation problem, and then we sort of had it for our original problem over here. And then the point is that if I reduce mod, so we have here R infinity chi v mod lambda acts on M infinity chi v mod lambda. But these spaces are isomorphic to M infinity mod lambda and R infinity mod lambda. And if you do the patching, you do it so that all these these diagrams commute. And then so we know, what do we know? We know that the support of M infinity chi v is a union of irreducible components of spec R infinity chi v. But the reason we worked with this auxiliary deformation problem is that this ring is irreducible. And now we're done because this implies that the support must be the whole spectrum. And if this is true for the whole module, it's true modulo lambda. And this is what we wanted to show. This is M infinity mod lambda, and this is R infinity mod lambda. So we're done. So we deduce. So we deduce that spec of R infinity is the support of M infinity. And so we don't just get. So this already gives us the fact that R is automorphic, but it also gives us that spec of the universal deformation ring is the support of the space of modular forms we started with. And another way of saying that is that the map from R to T becomes an isomorphism, at least after you pass to the reduction of the left-hand side. So the point is we know that this Hecke algebra is reduced. So we don't know a priori that the universal deformation ring is reduced, but we certainly get this. I'll just stop there. so I guess we'll take a 15-minute break.